Alright, time for another math easy solution. We're going to discuss the first derivative test. Basically, it's a series on how the derivative affects the shape of a graph. Well, derivative is just the rate change of a function. And so if you were to draw a graph like this, let's call this y, it's x. So basically, if you had a function like this, and we'll call this f of x. And then basically, when you look at where it's increasing, here, let's say at this point, if you draw a tangent line across this, as you can see, the tangent line is increasing here, so we'll just call this f of f prime is greater than 0 here. And also, as you can see, if you draw a tangent line where it's decreasing here, because remember, the derivative is just a rate change of the function, or basically the tangent line, or the slope of the tangent line. As you can see here, it's negative here, so then f prime is less than 0. And then from here, we could draw from this the increasing decreasing test. Yeah, which basically states that well, we have two conditions. If f prime is f prime of x is greater than 0 or positive, then it's increasing. And similarly, if f prime of x is less than 0 or negative, then the function f of x is decreasing. That's right, and this is f of x increasing. So as you can see from here. And then from this increasing decreasing test, we can get the first derivative test right here. I'll just write this down, which basically determines if you have a local max or minimum. Yeah, or neither of them here. So, but this one, you start off by first finding the critical point. So what this derivative test says is at the critical points, which I showed my other video what it was. Basically, at the critical points are points, let's say number c, so where x equals c, such that such a derivative at c is equal to 0 or doesn't exist. So what I mean by that is, if it's something like this, would be a local max, and then this would be f prime of c is equal to 0. Here this derivative is 0, or if it doesn't exist, if you have a sharp point like this, so then this one doesn't exist here, and this is a critical point here. This would be c as well. So if you were to look at these ones right here, and then the first derivative test has basically 3 statements. It states basically, if you have, let's say at the critical point c, that the function f of x goes from, f prime of x, let's say it goes from negative to positive, then this one right here, if it's negative to positive, it's something like this. Be going negative here, then positive here, that's the slope here. Then this one would be a local minimum here. Then this equals to local minimum. And then the second statement is basically, if your function f prime of x goes from positive to negative, then you just get a local max here. And this would just be positive like this, and it goes negative here. This is positive there, negative here. And then the third one is, if it changes from negative to negative or positive to positive, you don't have a local max or min. Yes, and you get neither of that. And this one looks something like this. This one would look something like if you had function goes like that. Let me just draw it better like this. So then this one here, this would be your critical point here, where the slope is 0. So c, and basically here this is positive here, and this is positive as well. So basically, if you illustrate all of them right here. So yeah, here I quickly drew the 3 different cases. Basically, case 1 is if you have both of them here goes from positive to negative. Actually, no, I got these mixed up. This is case 2 actually. This is case 2. This one's case 1. But anyway, so if you see from here, you can see that at c, this is the critical point here. This is f prime is 0, and this one's increasing and decreasing this local max. And this one's similar, it's negative to positive, this is local minimum. You could also download these notes on the info below. I have a Dropbox link to download these notes to be useful. And this one here, as you can see, there's no max or min in this case 3a, where this is a negative, and then this is positive, and this is positive here, and this one goes from negative to negative. And as you can see here, this one has no local max or min, and this one, both these have none either. So now let's look at some examples here of how to basically find the local maximum using the first derivative test. So if you have this function f of x equals 3x to the 4 minus 4x cubed minus 12x squared plus 5, and you want to get the local max or minimums here. Then we would use the first derivative test. First thing you do is just take the derivative here. So f prime of x, this one would equal to, well, this is using the power rule, bring the 4 down. This is 12x 3 minus, bring the 3 down. This is another 12x squared minus 24x. And so then, yeah, this one's 0, derivative of that. And now if we could simplify this further, we can keep going further. F x equals 2. Just take out the 12x out of there, just the common factors out. And this will get x squared minus x minus, this becomes a 2. And then you could factor this out further. This would just be 12x. This one right here would just be x minus 2 and x plus 1. Because if you were to times these out, basically, yeah, you need a number such that, you need two numbers such that they multiply each other equals -2, and they add up to become -1. That's this one right here. -2 times 1 is -2, and -2 plus 1 is this. Or you could, then if you multiply these out, this would just equal 2x squared plus x here, and then minus, because you're just multiplying both sides, just in case you didn't know this. And then this one multiplied out 2x minus 2, and then this would just equal 2x squared minus x minus 2. And that's just what we have right up there. Alright, so anyway, so this is our function right here. I'll just write this down again. F prime of x equals to 12x, x minus 2, x plus 1. So then now to find the critical points, we just have to set f prime of x to 0. And then as you can see from here, whenever x it's 0 at x equals to, well, it's equal to it when x is equal to 0 here. If you put a 0, it becomes 0. Or x is 2, if you put a 2 here, it becomes 0. And then last one here is if you put a -1 here, and that becomes 0. So we get our critical points here, because that's where derivative is 0. And this function is continuous because it's a polynomial, so we don't need to worry about where it doesn't exist, because derivative exists everywhere here. Well, first thing, let's just find out what the functions, let's just find out what f of x is equal to. I mean, f of, let's go -1 first. This one would equal to, well, 3 times whatever this function is. That's x4. So 3 times -1, 4 minus, yeah, so I just wrote this all down here. And then if you simplify this one, it becomes a +1. This is -1 because it's a cubed, and this is positive because it's squared. And then this would just be 3 plus 4, because negative times negative, minus 12 plus 5. This becomes equals to 7 minus 12 plus 5. 7 plus 5 is 12, so this becomes 0. 12 minus 12 is 0. And then I just want to quickly get these ones out as well. F of 2 is equal to, actually let's go f of 0 first. F of 0 is just 5, just put the 0 in everything. And then f of 2 is just equal to, well, 3 to 4. Okay, so you could put this in a calculator or solve it manually. I'll do it quickly here. What you could do, actually, just take out the 2 on the 2 squared, the common numbers here. So this just becomes times 2 squared minus 4 times 2 minus 12. I'm just taking the 2 out of there, so it's easier to calculate. This becomes 4. This becomes 3 times 4 is 12 minus 8 minus 12 plus 5. The 12's cancel, so we're equal to 4 times -8 plus 5. This just equals to -32 plus 5. This equals to, well, -27. So now if we were to just draw what we know out here, let's just go right here. Okay, so I drew the axes here, and then now we know that our critical points is at -1 here, is at 0, and this is at, let's go 1, 2 right here. These are our critical points, and we know that at this one, f of -1 is 0, so that's right there, and then f of 0 is 5, so 1, 2, 3, 4, 5. Let's draw it here. So this is 5 here. And now at -2, this is -27. So we don't want to see if these are local max or minimums. This one's all the way to here, 27 all the way to here. Okay, so we know that at these points derivatives are 0 here. We could just draw a line like this. This is derivative is 0 because it's going to be like that. This is 0 as well. So now we got to check on the intervals between this one less than -1 here to see if the derivative is increasing or decreasing, then similarly between -1 and 0 here, and from 0 to 2 and 2 or greater. So to do this, well, we first look at the function right here, our derivative function, which is, I'll just write this down below here actually. We have f of x is equal to 12x, x minus 2, and x plus 1 here. So now for our first interval here is going like this, where this is x is less than -1. So if you have x is less than -1 here, let's just make a table of this. So we'll have x is less than -1, and then if you were to put anything less than -1 here, you'll get this thing right here will be a negative, x minus 2. This would be negative as well, because if you put let's say -2 minus 2, that's 4, so we'll have a negative here. Now if you put this last one here, if you put less than a -1 here, let's say -2, this one is going to be negative as well. So then here we're going to have a negative times a negative, which is positive, times another negative. So then your f of x, so let's just write f of x here, this one's going to be negative, so this is decreasing here. And then so we're going to have actually something like this. So it's going to be something like this. So this one is negative, so we got this one. Now we have to look at between -2 and 0. So we'll have x is less than 0, greater than -1 here. So if we plug it in, just make a table here on the 12x, it's still less than 0, so this is going to be negative here. And then on here, it's still less than 0 here. Just put a negative in there, it's going to be negative. And now here, this one's going to be actually positive here, because this is going to be greater than -1. It's going to be positive here. So then this one's going to be negative times negative. This one is just, negative times negative is positive, and then times another positive is supposed to be positive here. So then here is going to go up like this. It's supposed to be 0, it's not. Okay, it's supposed to be like that. So we're going to have something like this. This is positive. And now if we look at negative, if with x is greater than 0 and less than -2, this one, if you look at this this side right here, this one is just going to be the +2. So if we put this is greater than 0, so this is going to be a plus. And similarly here, this one is less than 2, so the -2 is going to be a negative here. And then if we put anything plus here, plus, this one's going to be plus. So plus minus negative minus plus. If it's odd, it's going to be negative. The number of negatives, if it's odd, if it's positive. If it's even number of negative, it's positive. If it's odd number, it's negative. You can just look at it there. So this one's going to be negative here. So then this is going to be negative like this. This is going to be negative. So then if this is positive all the way up to here, so it's going to look something like that. And we could extend this actually all the way out to here, because it's always going to be negative. And then all the way to here. So now we have to see if at this point here greater than the 2. So now at x is greater than 2. Not 0. Now we just have to check what here. 12x is just going to be positive here. 12 is greater than 2. This is going to be positive as well. And this is going to be positive. So then our derivative is going to be positive. So then this would go up like this. And it would probably go continuous, because the function is continuous. You're going to have a positive here. And this is just right negative here. So as you can see here, there is our local minimum here. So we have this function here, f -1 is equal to 0, local min, and then we have f of 0 equals 5 equals local max, and then our final one here is just f of 2 is equal to -27 equals local min. Because we could see just looking at it, or you could see the first derivative test negative to positive. So basically whenever the sign changes, then it's going to be a local max or minimum, but if they're the same, it's not. In this case, we don't have the same. So we have something like that. So yeah, hopefully this helps. Here's another quick one just to show you that there is no local max or min if you have a function f(x) equals 2x cubed. Then from here we know that the derivative of f(x) equal 2, this is 3x squared, and then the critical point is just x equals 0. That's the only time it's 0. That's critical point. And then we know that f of 0 is equal to 0. Here's plug it in, 0 cubed, 0. So then if we plug it in right here, we know that this is going to be 0 as a critical point right here. This is x, this is y. And then, yeah, so if we plug it in, so if we look at the two intervals of, this is 0, of less than here and then greater than 0, so this one is x is less than 0, this is x greater than 0. We know that this is a function right here. We could do that same table thing or just look at it, but let's just do it for the sake of argument. So we have x is less than 0. If we put less than 0, this one's always going to be positive. So this is positive, so our f(x) is positive. And if we have x is greater than 0, again it's going to be positive because x squared is always going to be positive. So then this is going to be positive on both sides, so we're going to have something like this. And this is positive, and this is positive. And we have no local max or min. Yeah, so we have none of them here. So now if we graph this with Google, let's just graph this one first. So there's Google right there. Let's just plug this in, times x to the 4 minus 4 times x to the 3. Yeah, so we have the graph right there. As you can see here, it's the same thing as our function here. It goes down negative. There's a local minimum at that. And this is at 0, 5, local max. This is negative 1, 0, and then it goes to negative 27 here at 2, and it goes up exactly how our function is. So there's our function, and there's the one with Google. And similarly, the x cubed. Yeah, this one here, this one has no local max or min, as you can see from here. Yeah, and there's 0 as a critical point. It goes positive and goes negative. Well, that's all for today. Hopefully you learned about the first derivative tests, and basically it's a useful way of graphing functions and seeing how they are manipulated based on a derivative. Well, that's all for today. Hopefully you learned, and you can also download the notes I have below in the Dropbox link, and well, stay tuned for another math easy solution.